In today's class, we will briefly describe the closure properties available in CFL, and we will see some proofs, and some proofs I have left in the study material. You have to go through it because they are similar type of proofs. So I will be explaining one or two, and rest will be in the material only. You have to follow those. So let us begin. So what we are going to cover in this lecture is, firstly we will introduce an operation called substitution, in which we will replace each symbol in the string of one language by an entire language. Why we will start with this? Because if we can prove that this CFL is closed under substitution, and for your further reference I would like to say what closed means. You know already that if after applying, say one language is in CFL, and if after applying one operation it also belongs to the same language, that means if my original string is a context free language, and after substituting that string with some other things, and again the resultant is context free language, then we call it that this is closed under substitution. Fine. So we will begin with substitution, and we will prove that CFL is closed under, or context free language is closed under substitution. Then the other operations like union, concatenation, closures, and two or more, again homomorphism will be closed. We can prove all these operations are also closed under CFL using the theorem of substitution only. So if we prove if we can prove that it is closed under substitution, then rest goes fine, right? We do not need to struggle more. Fine. And so let us begin with substitution. Firstly, we will assume a set of alphabet as sigma, as we are doing from the beginning, and we are assuming every symbol A in sigma. Whatever the input symbol, we are generalizing it with a symbol A, and that belongs to sigma. Then we will choose a language LA, right? And this chosen language can be over any alphabets, not necessarily sigma and not necessarily the same. Why we are doing like this? Because we will choose an alphabet A which belongs to sigma, or whatever the content of sigma is, but we will generate some languages as LA which may not cover the symbols under sigma, because we will substitute those languages in my originally generating string, and will prove that this works fine. So that's why we are generating a language LA which not necessarily contain the symbols in sigma. It may contain some of the symbols, it may not contain. Whatever it is, we will see in our further slides, right? And this choice of languages defines a function S. We will use a function, it will be defined, the spelling is wrong here, fine, just correct it out. A function S, this function S is called a substitution on sigma, and we shall refer to LA as S of A for each symbol A. Means this symbol will be used to refer to all this throughout the proof. That is, we will use SA for further reference. You can see that we will use SA, right? Because we are using the function substitution. Fine. So now we are assuming one string as W, say A1, A2 up to AN. It's a string in sigma star, and SW is a language of all the strings x1, x2, xn, such that xi is the language on S of A1. So if W is a string A1 up to AN in sigma star, and SW is a language of string on x1 followed by xn, and that will be a string on the language S of AI. So you have to keep it in mind that this string xi up to x1 up to xn may contain the strings over sigma, may not contain the strings over sigma, right? As we have already mentioned in our first point, right? So in another way, we can put SW is the concatenation of the language is A1, A2 followed by SAN. Since we are mapping this A with S of A, so instead of writing like this x1, x2, xn, again we can say that we are substituting A1 with something, we are substituting a2 with something. So we can also say that SW is S of a1 S of a2 in this way. So you can say x1 is equals to S a1, x2 is equals to S a2 in this fashion, right? So you can use any one of the two, whatever you feel fine. So we can further extend the definition of S to apply the languages. SL is the union of SW for all strings W in L. So we will see how we are going to begin. So let us take one example. Suppose we are having one language that S0 is a to the power n b to the power n, where n is greater than equals to 0, and S1 is AABV. Fine. So if we say that S is a substitution on the alphabet 0 1, why? Because do not get confused that we are using A and B, but why we are writing it's a alphabet of 0 and 1. Just follow this one. In our previous slide, what we have seen, we have used the substitution like this: SA1 SA2. Why? Because the substitution was over the string of alphabets which we depicted as A, right? So here the substitution is for each and every symbol in the string. So what are the symbols present? Means wherever the 0 is going to be used in the string. Say we are having a string 0 0. So how we are going to replace 0 with? We will replace 0 with a to the power n, b to the power n can be anything, right? That's why S0 is one substitution. Means wherever the 0 symbol is, we are going to find out there with which value or with which string we are going to replace that 0. That is a to the power n, b to the power n can be anything, right? And wherever we will get 1, we will replace that with AA or BB, right? So these are the substitution languages with which we can substitute our original strings. Fine. Now language S0 is a set of string with one or more A's followed by an equal number of B's. You can see that S0, just we have described it again. What S0 is saying, that it is having whatever the number of A's and whatever the number of B's can be, both should be same. It can have again 0 number of A's, 0 number of B's, right? So equal number of A's and B's should be there for A then B, right? And S1 is a very finite and very small short language. It consists of 2 A's followed by 2 B's, right? Either 2 A's or 2 B's, or these two strings are possible, right? Fine. Now we are assuming our original string W as 0 1. So SW will be what? SW will be concatenation of S0 and S1, right? Since there, if you remember the previous slide, how we have broken, we have any language, x1 x2 and anything, any string, so we used SA1 followed by SA2. So similarly, what we are going to do, if W equals to 0 1, then SW will be concatenation of S0 and S1. So if you just combine this S0 and S1, what can be the combination? Say firstly we are combining a to the power n, b to the power n with AA, and then we are just converting a to the power b to the power n bb. So a to the power n, b to the power n bb can be written as a to the power n, b to the power n plus 2. The thing is same. Okay, now here n is greater than or equals to 1. Why? Because we have to keep at least AA and BB, because since we are just matching these two or concatenating these two, then n should be greater than or equals to 1. It's easily understandable. Fine. Now suppose L is equals to L0 star, that is a set of all string of zeros. Then if we restrict this to this one, then what can we say? SL, just remember here, instead of using both 0 and 1, we are using just 0. So we can replace this 0 star with S0 star, since just we are fine instead of writing this L equals to L0 star, we are just using the substitution functions. So it will be like this. Now S0 star means then this S1 part will be discarded. Now this language is a set of strings of the form A to the power n1, b to the power n1, a to the power n2, b to the power n2. We are just replacing with other variables, nothing else, right? You can see that if you just assume it in the form of integers, right? N can be 0, n can be 1, n can be 2, n can be anything in case of S0, right? So we are just writing in this generalized form. So it can include this kind of strings. You can just, if you substitute 0 in place of n, it will be empty. If you substitute first n equals to say 2, then it is AABB, right? If you substitute it as 3, then AABBB, and so on. So these are the various combinations possible. Now we will prove the theorem. This is, I think the concept of substitution is now clear to you. So how we are going to substitute our original string with some of the string which may not be a part of the origin, means sigma, right? Now we will prove that whether these two are equal, means whatever the substitution we are doing, whether after that substitution the language is CFL or not. So the theorem says, if L is a context-free language over sigma and S is a substitution on sigma, do not get confused that we are using the symbols of sigma. No, it's a substitution on sigma such that SA is a CFL for each A in sigma, then SL is a CFL, right? So if we can prove that SA, that is a substitution on on this sigma, whatever the symbols are there in sigma, if we are substituting with a substitution function called SA, and if we can prove that this SA is a context-free language, then we can say that okay, whatever the total substitution we are doing on the language, that is SL, is also context-free language. So this is our goal, we have to achieve it. Fine. So the essential idea is that we may take a CFG for L and replace each terminal A by the start symbol of A CFG for language S of A. So here the idea is that we will take one grammar, original grammar, and you can easily understand that in case of substitution we will be changing only the terminal symbols, rest will be the same, right? So we are assuming the grammar like this. If we are having one grammar, say V sigma P and S, and we are now assuming another grammar for substitution, it will be depicted as G of A, and we are using other symbols V A T A P A S A, right, for each A in sigma. Now, since we can choose any names we wish for variables, let us make sure that the set of variables are disjoints, that is, there is no symbol A that is in 2 or more of B and any one of the V's. So we are just using different variable names here, because the purpose of choosing such different variable names, that if two types of productions are there, say one set of production for G and another set of production for GA, so if we use two different kind of name for variable names for G and GA, then after when we will combine the production rules of G with GA, or whenever we will compare the two production rules, it will be easily understandable, because if we use the same variable name, then it is quite difficult to understand which variable belongs to which set and all. Okay, no more other issues. If you choose same variable name, so this can be one problem only. Fine. Okay, now we will be constructing a grammar G dashed having this V dash, T dash, P dash and S for SL. How we are going to do it? If you remember, we have chosen two grammars. One is G, that is the original grammar. Another is for using substitution, that is GA. So from that too we will construct a new grammar. Fine, that is G dashed. So in G dashed, what will be the variables? Obviously it will consist both the variables of G and GA. T will be again all the terminals of those two, right? Now P dashed, that is the production rule, it will consist of all productions in any PA for A in sigma and the productions of P, but with each terminal A in their bodies replaced by SA everywhere A occurs, right? Why? Because here our job is to replace the original symbols in the grammar with the substitution. So wherever we are going to find A, right, which is a part of sigma, or we are using the symbol A to represent the input symbols, that is covered under sigma, or the terminals, whatever you say, that we are going to replace with SA. So in the production P, PA is fine, but in production P we will replace A with SA because we are using the substitution form, fine. Now say if we are moving with an approach with the approach of parse tree, it is very useful here. So see that how it will be generating, that is totally depicted in the parse tree. Let us explain it. Here all the parse trees in grammar G dashed means a new grammar which we are generating start out like parse trees in G, right? Means same. See that what we are going to do, we are just going to replace A with SA, right, and nothing else will change. So start symbol will be same. So see that start symbol in our original grammar G was S, and in GA it was S as well. So we have started our parse tree with S only, right? But instead of generating a yield in sigma star, there is a frontier in the tree where all the nodes have labeled that are SA for some A in sigma. So I have already told you this one, that here if you draw the parse tree of the original grammar, so what it would have done, we would start with S and would like to generate a parse tree which would yield a set of strings, say W, consisting of the alphabets over sigma, right? So say you are given to generate a string say 0011, so you would start with start symbol, then use the production rules and keep on drawing the parse tree, and it will stop when it comes with the string 0011. But here our job is not that. Here what we are going to do, here at the same time, okay, we will generate the parse tree, but at the same time wherever we will encounter any symbol A in sigma, we will replace that with S of A. Just see the same thing has been done. Say S is generating say A1, so we are going to replace that with SA1, right? So we are substituting continuously. So that has been depicted in the parse tree, right? So then dangling from each such node in a parse tree of GA, those yield is a terminal string that is in the language SA. So how this has been generated, this first step, I think that is clear. So from S, instead of generating directly the strings that belong to sigma, we have used the substitution with it, right? So now see, then a string W is in LG dashed if and only if W is in SL, right? So whatever SL means what? After using the substitution for each and every symbol A which belongs to sigma, we will come up with a language SL. So then W, whatever the string is, original string, will be in the newly generated grammar if and only if whatever the string we are working on is in SL, right? So if we can prove that okay, this string W is a language of whatever we have achieved after substitution, then only our string will be in LG dashed, right? So how that are possible? It is possible if we are supposing the W is in SL. Then what should be the approaches? Then there is some string X which consists of A1, A2 up to N is in L, and the string Xi is in S of A1 for I equals to this, such that W equals to X1, X2, Xn, right? So if this mapping is possible, say we are having a string X, we are denoting it with A1 up to An, it will be in L, and string Xi is in S AI, such that W will be equals to this one X1, X2, Xn, right? Since because we are substituting it, so it should map, it should get matched, right? Fine. So then the portion of G dash that comes from the production of G with SA substituted for each A will generate a string that looks like X, but with SA in place of each A. This string is SA1 A2. I have told you already, because in place of this, A1 A2 and all, we are just substituting SA1 A2 and so on. So this comes in the upper part of the triangle. So if this is possible, this substitution is possible, then we are one step forward towards the proof, because we are substituting with this one, and my parse tree can generate it. So this is done. Now, since the production of each GA are also the production of G dashed, the derivation of x1 from SAI, xi from SAI is also a derivation in G dashed, right? So if the production of GA are also the production of G dashed, then xi, whatever we can derive from SAI, that is xi, it will also be a part of production of G dashed, right? Since all the productions of GA are already a part of the production of G dashed, so this production will obviously hold. Fine. And the parse tree for this derivation is suggested by the lower triangle. Just see, since we have already incorporated all the production of GA into G dashed, so SA1 can generate x1, SA2 can generate x2, and so on and so forth. So all these are part of G dashed only. Now, what is the only if part? Now suppose W is in LG dashed. Okay, we claim that the parse tree for W must look like the tree of the figure, this figure. The reason is that the variables of each of the grammars G and GA for A sigma are disjoint. Thus, the top of the tree starting from the start variable S must use only the production of G until some symbol SA is derived, and below that SA only productions of the grammar GA may be used. So we are successful in combining these two, because at the top portion we are using start symbol from the grammar G, and then we have, instead of using directly the productions of from S, that is what belongs to G is, we have successfully substituted with the grammars of that belongs to GA, right? So we have combined the two well. Fine. So as a result of combining these two, what happens? Say we are having a string A1, A2 up to AN is in LG, and the string XI is a language of S of AI. So such that what happens, if W equals to x1, x2, xn, and the string is A1, A2, AN is the yield of the tree that is formed from T by deleting some subtrees, means we have deleted the original productions of from the G, and we have substituted with this substitution strings. And again, this string x1, x2, xn is in SL, since it is formed by substituting the string of xi for each ai. Thus we have concluded that W is in SL, right? So we have come to the resultant by substituting this one, by substituting this A1 with x1, SA1 with x1, SA2 with x2. So this and we have generated the tree fine with no problem, right? So we can say that my W is in SL, because see, the W is the strings of x1, x2, xn, and we have got this string from substitution only, SA1, A2 and all. So we can conclude this belongs to SL, right? Now I'm not going to discuss all this thing again. So we have proved that the substitution is closed under this context-free language. So you can just go through the slides, and you can easily understand that it will be closed under union. Why? Just for your purpose, if I assume any language 1, 2, so how you are going to do it? You will substitute that. You will assume S1 as L1, S2 as L2, and follow the property of substitution. Union will work. If we go for concatenation, again say 1, 2, what we are going to do? Same, it will be same like the union, right? So we will depict it as L1 followed by L2, again if we substitute the original language 1 to with L1 followed by L2, again substitution will work here. Similarly it will be for closure and positive closure, that is if we having one language 1 star, we can use S1 as L1 and can follow similarly, and for plus the same thing will work, right? And same for homomorphism. You can just follow the study material or the book which we are referencing. You can see some examples there, and if you are done with this substitution property, then these are the subset of that only, right? Okay, now one another more property is that reversal, right? So this reversal cannot be done with substitution because it is a total reversal of each string. So we can follow the process of induction to prove this one, that this CFL are closed under reversal. So you can see here we are considering one grammar as G as V, T, P and S. So what will be the grammar for reversal? Same thing will remain, only the production rule will be the reverse, right? Other variables, terminals, start symbol, everything will be same. That is how it will work. Say production rule will reverse means if we are having one production A derives alpha, then in the reversal grammar it will be A derives alpha reverse, right? So you can use the method of induction. We have used it several number of times for base condition. You can take one example and you can assume one production. You can take the base rules, right? And you can prove that okay, if this holds, the reversal also holds for one length string, and for n length string how we are going to prove it off. Okay, so let us see another thing, intersection with regular language. If we intersect context-free language with regular language, how it will work. We will see this with an example, and proof we have to consult the study material for it. Okay, so we are assuming this one, if one language L, that is 0 to the power n, 1 to the power n, 2 to the power n, is not context-free language, you know that. However, these two are context-free languages, that L1 0 to the power n, 1 to the power n, 2 to the power I, and 0 to the power I, 1 to the power n, 2 to the power n, because here we are comparing 0 with 1 in first case, and in the second case 1 with 2. So here 3 comparisons are not there, it is restricted to 2 comparisons only. So this is context-free language. So if you convert the first L1 language to grammar, it will be like this. I am not going to details. We have already done several exercises for converting a grammar to a language and converting a language to a grammar, so you can easily understand it how we have done it. And if we convert this L2 to this one, it will be like this. And fine, so now we will see that what intersection results. Now if we are assuming on language L where L1 and L2 are intersecting with each other, L1 requires that there be the same number of zeros and ones. In L1 it is there, while L2 requires the same number of ones and twos to be equal. So a string in both the language must have equal number of all the 3 symbols, right? So it should have equal number of 0, equal number of 1 and equal number of 2, if we find out the intersection part only. So if the CFLs are not closed under intersection, then we would prove the false statement that L is context free. We conclude by contradiction that CFLs are not closed under intersection. On the other hand, there is a weaker claim we can make about intersection. The context free languages are closed under operation of intersection with a regular language. So what is the meaning of it? See, if we move in this path, that we have assumed L1 as containing equal number of zeros and ones, and L2 containing equal number of ones and twos. So easily you can see that intersection of these two will be equal number of zeros, ones and twos. So is this a context free language? No, not at all, because using a PDA we cannot compare 3, right? It is possible to compare 2 only. Why? Because say we are comparing number of zeros with number of ones, we can push zeros, and whenever we get 1 we will keep on popping each and every 0. If these two are same in counting, then we conclude that okay, the number of zeros and number of ones are equal. If not, we will conclude that no, the number of zeros and number of ones are not equal. But what will happen with 2? So if we have pushed on encountering 0 and we have popped on encountering 1, our stack will become empty, but still 2 remains. So we cannot compare the number of 2's with zeros and 1s. So 3 comparisons are not possible with a single stack memory, right? So this will not be CFL. On the other hand, there is a weaker claim, means in special cases you can see that the context free, if we combine one regular language with one context free language, and if we find out the intersection of it, say 0 to the power n, right, is a regular language, and we are having one context free language that 1 to 0 to the power n, 1 to the power n. So what is the intersection of these two? 0 to the power n. So this is a context free language. So these are the examples where if we intersect a context free language with a regular language, in most of the cases it will be a regular language only. So that will also be a context free language also. So these are closed under this operation. However, there is a proof, generalized proof. You can just consult the study material which I will be sharing with this lecture only. There I have proved it off, and you can follow it from there. Okay, we have to see more properties. There are 3 languages, L1, L2, L1 and L1 and L2, and a regular language R. So what are the outcomes if we subtract this regular language from a CFL L? Then it is a context free language. Okay, and if we are having one language L, and if we are finding out the complement of it, it is not necessarily a context free language. It may be a context free language, it may not be a context free language. In which case it will be a context free language, we will see in the next slide. And if we subtract L1 from L2 from L1, it is again not necessarily context free language. These are special cases. In some cases it may be a context free language, in some cases it may not be. Okay, you cannot say okay, this is closed. This is closed under certain specific condition. So for one, whatever the first point says, if L minus R is there, so can we write this, that we are subtracting the regular language from the context free language L. So what intersection we will be getting after subtracting R from the original set? We will be remaining with R dashed, so it is L intersection R dashed. And we know that regular language is closed under complementation as well, right? So if R is a regular language, R dashed is also a regular language. So L intersection R will be what? It will be obviously a regular language, or in a broad sense it is a context free language, right? So if we subtract L from R, so what remains? Context free language remains. It may not be regular, right, but it will be a context free language, so it is closed under this L minus R operation, right? So find the second one. I told you that it not necessarily holds, but in which case it may hold. See, if we choose this one, L1 intersection L2, so we can write this one L1 complement union L2 complement whole complement. Fine, it is De Morgan's law, nothing else. And we know CFL are closed under union, right? And it means if we punch these two, how we know that CFL are closed under union? Because we can prove this by using the substitution property. So if L1 and L2 are context free language, the union of that two will also be a context free language. So if you can write in this form, if you can depict L dashed in this form using two separate language and finding out the intersection of it, then it will hold. Otherwise it may not work, right? If we finding out the complement part, it may not be the context free language always. Okay, lastly what we are having, see, we know that sigma star is a CFL for every alphabet sigma. Designing a grammar for PDA. Now if L1 minus L2 are always a CFL, then L1 and L2 are, it would follow that sigma star minus L was always a CFL, right? So if we if we can find out this one, that L1 minus L2, if it is a CFL, then obviously both L1 and L2 should be CFL, right? And if we are finding out any language which we can discard from sigma star, then it will become a CFL, because we are finding out two languages, L1 and L2, both are CFL. And if this follows, then original language L, we have to subtract it from the sigma star only. And however, sigma star minus L is what? L dashed. When we pick up the proper alphabet sigma, thus we would contradict 2, right? And we have proved by contradiction that L1 and L1 minus L2 is not necessarily a CFL. So if we firstly, if we assume that L1 minus L2 is a CFL, and we have assumed that both L1 and L2 are CFL, so this is possible if we find out any language L by subtracting it from the sigma star, but this is not possible because we have to consider the strings which are under sigma only. So if this cannot hold, right, always. So if we subtract two different CFLs from one another, it may not be a CFL, but still I am saying in some special condition this may hold as well. If you subtract one language CFL from other CFL, it may result to a CFL also. Fine. So the last property which we will be discussing today is the inverse homomorphism. So inverse homomorphism, if you do not remember, you can find it in the lecture of regular language. There inverse homomorphism has been explained. And if L is a language, then H inverse L is a set of strings W such that H W is an L. So without further going to more details, we will use an PDA to prove it off. What we are doing here, we are assuming one PDA. Say P, it has Q, T, tau, delta, Q naught, Z naught, F. You know the meaning of each and everything. That accepts L by final state. Now we will construct one PDA P dashed using the previous PDA P, and we will use some mapping of homomorphism. Just see, we are using this one, a new set Q dashed. Then instead of terminal T, we are using sigma because we will restrict some symbols here. Then in place of delta, we are using new production delta dashed, and in Q naught we are using Q naught comma empty string, and this all follows, right? Because see here, final state is there, and again empty symbol is there because it may also get accepted by the emptying the stack, right? So that's why we are using epsilon as well with it. Now what is Q dashed? Q dashed is a set of pairs of Qx such that Q is a state in Q and X is a suffix of substring H of alpha for some input symbol, H of A for some input symbol A in sigma. So what X is ultimately, X is a set of strings which we have not encountered till now. It is the remaining set of strings which we are going to push into the stack for our further operations. Okay. Now the first component of the state P dashed is the state of P, right? We will begin with the same thing, and the second component is the buffer. In the buffer we are storing something, and from the first component means we will begin with the same start symbol as that of P, and then we will move to the buffer. In buffer it is stored, and we will use each and every symbol in the buffer, and we will keep on processing. So we assume that the buffer will periodically be loaded with a string HA, and then allowed to shrink from the front as we use the symbols to fit the simulated PDA-P. Note that since sigma is finite, HA is also finite for A, and there are a finite number of symbols for the state P dashed. So what we are doing ultimately, so whatever the strings were there in sigma, so we are keeping it in the periodically using HA in the buffer, means whatever the function of homomorphism we are using here, that will be stored in the buffer, and we will keep on processing the strings from the buffer only. Okay. Now what this transition function defines, so if delta dashed is Q comma epsilon a and x, then if we map it to the form of homomorphism, it will look like this. Just see that for any state q and for any input a and any stack symbol x, we will move in this fashion, right? And when the buffer is empty, p dash can consume its next input symbol a and place ha in the buffer. So when buffer becomes empty, it is again going to put something into the buffer, that is the next input symbol a, and it will use the function ha and will place it in the buffer only. Okay, so you can see again we are using the substitution only here, right? So in place of a, we are using a function called homomorphism, and we are placing that function in the that output in the buffer, and we are processing it, and ultimately we will see that my PDA, my newly designed PDA, that is p dashed, can work on it. So if it can work on the newly processed string or newly substituted string, then both the thing are same, so it will be closed under inverse homomorphism, right? Same the substitution theorem, nothing else. Okay, now if this condition holds, if this is the input qbx and it contains a pair p lambda, b is a terminal, it may be a terminal string or it may be empty. So it will how it will going to work, p dash always has the option of simulating a move of p using front of its buffer. If b is a symbol in t, then the buffer must not be empty, but if b equals to empty or empty string, then the buffer can empty. So we are doing what? We are doing the mapping only, right? So here if this b is a terminal symbol in t, right? So if it is a terminal symbol in t, then the buffer should not be empty. So there must be something which we are going to process, and if it is empty, the buffer will be empty. So both the condition works fine. Now the state p dashed is q naught followed by empty string, that is epsilon. You have already defined it, and p dash starts in the start state of p with an empty buffer. Firstly the buffer was empty, and after that we have processed each and every symbol a and have applied the homomorphism, inverse homomorphism function, that is h inverse function, and we have moved off into the buffer. So likewise the accepting state of p dash, those states q epsilon such that q is an accepting state of p. So here, since the start symbol are same and we have mapped all the other symbols encountered in the terminals with our homomorphism function, and then q, if this is the in p dash, if this is those states are q comma epsilon and q is the accepting state of p, so in both the cases in p and p dash it will get accepted, right, after processing all the strings. So if we can write in more generalized form, so this is the form where it will start with the original start state q naught and apply the homomorphism function h of w, and if this works, then how it will work, if it can process this total string w and can go to the accepting state ultimately, then this will work only, right? So the proof in both directions are induction on the number of moves made by the two automata. In the if portion, one needs to observe that once the buffer of p dash is non-empty, it can read other input symbol and must simulate p. If it is non-empty, it is just going to copy p, right, until the buffer has become empty. Although when the buffer is empty, it may still simulate p, right? Now once we accept this relationship between p test and p, we note that p accepts hw if and only if p test accepts w. So if you remember that process of converting that emptying PDA to acceptance by final state, it is more or less like the same. Here we are just not moving from one approach to other. Here we are showing that if p dash can accept w, then if p gets accepted by the final state, right? So the thing is same. So in more generalized way, so what we can write, L of p dash is the inverse function of L of p, right? So means the in the homomorphism function, we can, using the homomorphism function, we can just write this process by the substitution rule, that is the new PDA, the language gets accepted by the new PDA p dashed is the same substitution function of L of P of the original PDA. Right, so this homomorphism function is also closed under inverse context free languages, so this also holds. Fine, and this much for today's lecture. In the next lecture we will just go on some properties called decision properties of CFL. Thank you.